in the test, in the null hypothesis HO, you have only one restriction about the regression coefficient, which is beta z. Okay, we have only one restriction, and for the testing and this one, we are testing the individual effect. Okay, the individual effect of one independent variables on the independent variables. Okay, all right, and we have one restriction in the null hypothesis here. Okay, and for this one, you may use confident interval approach. You may use the test of significant approach, and you can also use the p-value approach to test for an individual regression coefficient. All right. Okay, and okay, remember that here we are testing the individual effect of one independent variables on the dependent variables. Okay, and we have only one restriction, in the null hypothesis. Okay, and in that case, we will use a t-test. Okay, or we take advantage, we make use of the t-distribution to test for a single or an individual regression coefficient. Okay, now today we will start our lesson, our lecture today, with the test of multiple restriction in the null hypothesis. Okay, which means that we will test the joint effect, not the individual effect of one independent variables, but the joint effect of many independent variables on the dependent variables. So what is the joint effect? Okay, joint effect here mean that, all right, so last time we talked about the explanation of each individual independent variables on the dependent variables. We may have this one as the dependent variable y. Okay, and then we have x1 as the first dependent variables to explain for y. Okay, and this one is the information that x explain for y. Okay, and we may have another independent variables in the model, like this one, x2, and there's maybe a correlation. This part, there may be a correlation between x2 and x1. That's why we have these two circles intersect with each other like this. So this part, the pink area here, we say that is the individual effect, okay, of x, okay, on y, of x1 on y. The yellow area here, we call it the individual effect of x2 on y. And this area, the black area here, is the effect, is the information that x1 and x2 both explain for x and y. So the combinations, okay, the combination of the pink, yellow, and black area here is the joint effect of x1 and x2 on y. Okay, so now we will test whether some independent variables in the model can explain significantly for the value of the dependent variable y. Okay, and we call this, what is it? And we call this part, okay, the pink, the combination of pink, yellow, and black area here is the joint effect of x1 and x2 on y. Okay, now let's test for the joint effect of regression coefficient, or we say that the joint effect of some independent variables on the dependent variables. Okay, we also call this test the multiple linear restriction in a regression model. Okay, now, and for the test, and this test, okay, this test will deal with a number of regression coefficients in the null hypothesis, not only one regression of coefficient, but we will have multiple, we will have many regression coefficients in the null hypothesis, and we will not have one restriction anymore, but we will have multiple restriction in the null hypothesis. For the test, the John effect for linear restrictions test here, we will have two types of tests, which is the test, the overall significance of the sample regression model, test the overall significance of the model, and also we want to test the John effect of some variables, the John significance of some variables in the model. Okay, there may be, all right, there may be some, when you do the t-test, you may see that some variables do not have the individual effect on the dependent variables. Okay, but the combination of them may have the joint effect on the dependent variables. Okay, that's why we may want to test the joint significance of those variables to the dependent variables to see whether they explain for the dependent variable. Okay, so that is the type of test we test the joint significance of just some variables in the model. Now, because here we deal with many regression coefficients in the HO hypothesis. That's why we cannot use T distribution anymore. And it is proven that a test statistic that can test for the null hypothesis will follow of F distribution. That's why for this test, we will not use the t-test anymore, and the test that we use in this part will be an F test. Okay, so now let's look more detail on what we will do here. Okay, the first one, test for the overall significance of the model. All right, so our purpose in designing the model is to explain for the dependent variable y. Okay, so a model is called significant. Okay, is said to be significant when it can explain for the dependent variables in the population. Okay, which means that those independent variables in the model has an effect, okay, actually significantly has an effect on the dependent variables in the population that we are interested in. Okay, so here we will test the hypothesis like this for the overall significance of the model, not the significance of one regression coefficient, but this is the significance of the overall model. Okay, now what will be our hypothesis? And look at this. We have the non-hypothesis HO. Okay, we have weight beta 0 at the same time equal beta 2 equal so on and equal beta k, and they all equal to 0. Okay, although here we have only one line for the non-hypothesis, but look at it more carefully, we will see that there are many restrictions here. Okay, we have restriction beta 1 equal to 0. We have the restriction beta 2 equal to 0, and so on to beta k equal to 0, which means that we have k restriction in this non-hypothesis. That's why we call this test a multiple linear restriction test. All right, and the null hypothesis state that all of the regression coefficients are simultaneously equal to zero, which means that they are all equal to zero at the same time, which means that all the independent variables in the model do not have any effect on the dependent variables, which means that none of the independent variables can explain for the variation in the dependent variable. All right, so our alternative hypothesis here, H1, is that okay, so these regression coefficients are not equal to zero simultaneously, which means that at least one regression coefficient is different from zero. Okay, so that's why we may have this sum beta 0 square, beta 1 square, beta 2 square, and so on to beta k square. Though they are different from zero, or more exactly, they are greater than zero. Okay, all right. And remember that for the test, the overall significance of the model, we do not have the intercept. Okay, the intercept, the constant in the null hypothesis. In the null hypothesis, we are just testing the slopes of the model, the regression coefficient, not the intercept. Okay, that's why we do not have beta 0 here. Okay, we are just test the effect of the independent variables in the dependent variables. That's why there is no intercept here. Okay, all right. And for this one is the hypothesis for the overall significant test, and the non-hypothesis, as you see that all the regression coefficients are simultaneously equal to zero, which means that all the independent variables jointly do not explain for any variation in the value of the dependent variable y. Okay, which means there's no joint effect. Okay, there's no joint effect of the independent variables in the model, which means that the independent variables in the model does not do not explain any variation of the dependent variables. Okay, and this also means that the ESS, okay, the explained sum of square, okay, the variation in the value of the dependent variables that is explained by the model ESS, okay, it is equal to zero. Yeah, ESS is equal to zero because the independent variables cannot explain any variation of the dependent variables. Okay, that's why we have the coefficient of determination R squared here is equal to zero. Okay, so instead of using this hypothesis, you may want to use the equivalent one, okay, the equivalent one to test for the overall significance of the model. That is, we have HO, the non-hypothesis, is that the coefficient of determination R squared is equal to zero, and H1 R squared is greater than zero, which means that the model do explain for the variation in the value of the dependent variables. And remember that R squared that we are talking about here, okay, R squared in the hypothesis here, so will show is the R squared of the population regression model, not the R squared of the sample regression model. Remember that. Every parameters in the model, okay, every parameters in the hypothesis are the parameters of the population model. Beta here are the slope, the regression coefficient of the population regression model, and R squared here is also the coefficient of determination for the population regression model, not the sample regression model that you can calculate from the sample data. Okay, this one. So how the population regression model fit the population data. All right. Okay, so to test for the overall significance of the model, you can use either this one, okay, this hypothesis. You can use this one. You can also use this one to test for the overall significance of the model. Now, to test for the overall significance of the model, we will do the following. We will follow the following steps, okay, like just like a t-test. But now, as we say before, we cannot use t-test anymore because the null hypothesis is dealing with many regression coefficients. Okay, so here we will use an f-test. Now look more detailedly what the f-test we are using. Step one, all right, we have to state the hypothesis. Okay, for every test, the first step is to state the hypothesis. Remember that. Do not forget the hypothesis. Okay, and step two, and about the hypothesis we have just discussed before, you can say you can use either the hypothesis we have discussed, maybe about the betas or maybe about the R square. Okay, now step two, you have to calculate the test statistic. But the test statistic here is not a t, observed t, but it is an observed f value. Okay, so the test statistic is calculated as this one, and it's proven that it can test for the null hypothesis. We will not go into detail how this one can test for the null hypothesis. Okay, we will just know that this one can help us to test for the hypothesis. Now, f test here, the observed value of f. Okay, here we have the observed value of f. It is equal to ESS divided by its degree of freedom, which is k, the number of independent variables in the model. And in the denominator, we have RSS, the residual sum of square, divided by its degree of freedoms, which is n minus k minus 1. Okay, so if we divide it, both the numerator and denominator by t at s. Okay, we divide t at s for both the numerator and the denominator. Then we will have here, okay, it is equal to r squared divided by k, and in the denominator we have 1 minus r squared divided by n minus k minus 1. So rewrite the test statistic here. Okay, rewrite the test statistic. We have f, the observed value of f. Okay, the test statistic is equal to r squared, the coefficient of determination of the model, divided by k, okay, and over 1 minus r squared divided by n minus k minus 1. This is our f value. And this one will follow an f distributions with the degree of freedom of k and n minus k minus 1. Okay, remember that for an f distribution, we have 2 degrees of freedoms, which is the degree of freedoms of the numerators and the degree of freedoms of the denominator. Okay, so this one is the degree of freedoms for the numerators, and this one is the degree of freedoms for the denominators. Okay, our f here will follow an f distribution with the degree of freedom of k and n minus k minus 1. All right. Okay, so just rewrite this one. We will have our f, observed value of f, will be r squared times n minus k minus 1 and divided by 1 minus r squared and time case. Okay, all right. So now look at this. Look at the the observed value of f. So what will happen? What will happen if the null hypothesis is true? Now, what will happen if the null hypothesis is true? What will be the value of f if the null hypothesis is true?
0.
0. Yeah, exactly. If the null hypothesis, our null hypothesis here is that r square is equal to 0. So if the null hypothesis is true, then our f here will also be equal to 0. Now look at the distribution of f. Okay, so here is our f, and this one is the probability of it. The distribution of f will look like this. It is not a symmetric one, and the value of f is also always equal or greater than 0. So if the null hypothesis is true, then our f value will be equal to 0 like this. So now, if we want to reject, the null hypothesis, our observed value of f must be very different from 0, which means that it will be far away. It will be far away from 0. Okay, it must be far away from 0. It must be very different from 0 so that we can reject our null hypothesis. Okay, but if the observed value of f is close to 0 like this, okay, then we cannot reject the null hypothesis at all. Okay, so it means that here we must have the value of the fs, of the observed value of f, as different, very different from the from zero, which means that it is maybe stay away from zero like this. So how far enough, so that how far enough from the observed value of f to zero so that we can reject the null hypothesis. So here in statistic, okay, in statistic and probability, we have a milestone which is f alpha, the critical value, of f. Okay, like we have the critical value of t, here we also have the critical value of f. Okay, we call it the f alpha, okay, the critical value of f, so that the probability that we can observe any f value greater than this critical value is alpha. Okay, we call this one the critical value f alpha. Okay, and then that if we have the observed value of f is different from 0 enough, is far away from 0 enough, which is it must be greater, okay, greater than the critical value, greater than this point. Okay, at that case, okay, in that case, we can reject the null hypothesis, which means that fs here, if we have fs is greater than the critical value, that is f alpha, okay, we say that, all right, so the observed value of f is different enough compared to 0, also it is far away, is far enough from 0 so that we can reject the null hypothesis. All right. Okay, so the decision rule here is very simple. As long as we have the observed value of f here is greater than the critical value of f, then we can reject the null hypothesis as that is r square is equal to 0. All right. Okay, so step 2 here we will calculate the test statistic. In step 3, you will find the critical value of f. Okay, by finding, in order to find the critical value of f, you can use the distribution table, F distribution table at the appendix of the book, or you can also use Excel to find the critical value of F. Now, in order to use Excel to find the critical value of F, you can use this function like this. You can use the function like this. Okay, you can use this function. We have F, we have F, the function F dot NIV, okay, dot right tail. Remember that F test is one-sided test, okay, and we test to the right of the F distribution. That's why here for the critical value, please use the function F dot INV dot right tail. Okay, and the parenthese you will provide information about the level of significance and also the degree of freedoms for the numerator and the denominator. Okay, for example, we want 0.05 as the level of significance. The degree of freedoms for the numerator will be maybe 3, okay, and the degree of freedoms for the denominators maybe 45, for example. Okay, then we will have this one 2.812, okay, as the critical value of F. All right, now that is how you can find the critical value of F in Excel. You can also find the critical value of F in the F distribution table. Now, where is that? Here we have, okay. Here we have the F distribution. Where is it? Here. We have the F distribution here. All right. So you just have to look for the, here we have this one. Percentages. 1% and 2%, 1% and 5%. Let me see. Table D3, but is it an the distribution for the level of significance 1% or 5% here? So here we have the degree of freedom for the numerator N1, and this column, this is the rows here, and the column here is the degree of freedom for the denominator. Oh, okay, good. Here we have probability here. We have the level of significance here. Okay, so if the level of significance is what is it? 0.1, 0.05. We for the degree of freedoms, yeah, we also have 0.5, 0.01 here like this. Okay, and also we have 0.1. This one may not be used because the level of significance is too high. Okay, so just look at it. For example, I want to, all right, for example here, I want to find the F statistic, the critical value of F for 0.05 level of significance. The degree of the numerator is 3, and the degree of freedoms for the denominator is 45, for example. All right, now look at this table. This one is the degree of freedom for the numerators, okay, 3, this column, and we need the degree of freedoms for the denominator is 45. Here we have 20. Oops, 20. Do we have? And yeah, we have here. Oh, now we do not have 45, but we have 40. Yeah, 40 and 60. Okay, so maybe we will take a number around this, around the value of 40 and 60. Now look at the column here, the column for 3, which is the degree of freedom for numerators, 3. Now, if the degree of freedoms, now we look at this round for 0.05. Okay, we have the critical value here is 2.84. For the 60, look at this round, we see that, okay, the critical value of f here is equal to 2.76. Okay, so we might want to take a number between these two. And because 45 is close to this one more, so the value must be maybe 2.8. Okay, 2.8, which is closer. Okay, and the actual value that we can find by using by using Excel here is 2.8. Okay, 2.812. Okay, which is very close to the value that we can calculate using this a value at the median. Okay, a value between these two values, 2.84 and 2.76. Okay, all right. So that is how we can look for the critical value of f in the table. But more easily, as we have the laptop, okay, you can use Excel. It's very quickly to find the critical value of f. All right. Okay, so now our conclusion is here. If the observed value of f here is greater than f alpha, the critical value, then we can reject HO. And if it is not, then we will not reject the null hypothesis HO. All right. And we also have another way to do the test by using the p-value approach. We may want to use the p-value approach like we use for the t test. Okay, so let me say that. So the f, where's my, yeah. So like we say, for f distribution, we will find the critical value of f. Okay, this f0 and f of f. So we will find the critical value of f by this way. Okay, so if we have an f star here, so that the probability that we can see an f that is greater than f star is alpha. So we will call this one the critical value f alpha. So alpha is the area to the right of our critical value of f. Okay, so here p-value for the observed value of f will be determined by the same way. So if here is our observed value of f, then the area to the right of the observed value of f will be the p-value for it. So here, if this is our f alpha, for example, okay, then in this case, we have fs is greater than f alpha, and also we have p-value is smaller than alpha. Okay, so in this case, if p-value is smaller than alpha, then we will reject the null hypothesis. And if the p-value is not smaller than alpha, then we cannot reject the null hypothesis HO, which means that in the case where we have, all right, we have alpha is here, F alpha is here, for example, then we will have p-value in this case is greater than alpha. And in that case, we cannot reject the null hypothesis. Okay, so the same rule as we use for the t-test. As long as p-value is smaller than the level of significant alpha, we can reject the null hypothesis. All right. Okay, so that is the test, the overall significance of the model. Now, let's do an example. Okay, where's my example? All right, so I will open starter. For example, I may have a example here. All right. I have a set of data including bus travel, which is the transportation by bus in some urban area. We have fare, which is the bus fare, and gas price is the price of gas. And we have income here is the average income per capita in each area. We have population here is the population in area. And density is the population density, and land area is the area of the city. Okay, so I want to use those independent variables to explain for bus travel, which is the urban transportation by bus in cities. Okay, so I want to rank bus travel by okay, by fare, gas price, income, pop, maybe land area. Okay, enter. All right, so I have this one. We have this one is the estimation output. We have the estimation output here. All right. Okay, so please test for the overall significance of this model. Is this model significant or not at 5%? 5% level of significance. Okay, now please follow step that we have just discussed. Test for the overall significance of this model. Okay, at 5% level of significance. Test for the overall significance of this model. Any volunteer? Any volunteer have me to test for the overall significance of this model? Okay, so Đức Mạnh, I see your hand. All right. Do you have any encouragement point yet?
Yes, I had one in my voice.
One. All right. So, okay, now we may want to give the chance for a student that haven't had any uh, encouragement point yet. Okay. All right. So, Bảo Anh, do you have any encouragement point yet?
Not yet.
Okay, good. So let's do this exercise. All right. Okay, so we want to test for the overall significance of this model. How can we do that?
The first step is to establish the hypothesis.
Okay, oops, reconnect. Okay, so our first step here. All right. First step is to state the hypothesis. What is the hypothesis for the model here?
Is beta 1 equals to beta 2,
1 equal beta 2,
beta 3,
beta 3,
beta 4, and beta 5, and then equals to 0.
Yeah, we have 5 independent variables in this model. So we have 5 slopes here. Okay, we have beta 1 to beta 5 all equal to 0. Okay, now what about the alternative hypothesis H1?
Is beta 1 squared
Beta 1
plus
square plus
beta 2 squared
yeah,
plus beta 3 squared
yeah,
plus beta 4 squared
yeah,
plus beta 5 squared, and then is not equal to 0.
yeah, is not equal to 0, or we can say that is greater than 0. All right. Because this one is a sum of square. So if it is not equal to 0, then it must be greater than 0. Okay? So now what is the second step?
We then calculate the test statistic.
Yeah, we calculate the test statistic. Now what is it?
Is Fs equals to R squared
Yeah.
over K.
Okay, you can rewrite it as like this.
And
Multiply times n minus k minus 1 and divided by 1 minus r squared times
K.
k. Yeah, and just plug in the number. What is r squared of this model?
uh, 0.9119.
Yeah, 0.9119. We have 0.9119 times
Uh,
n.
34.
Yeah, we have n here is 40. 40 minus k, which is equal to 1, 2, 3, 4, 5. Okay, 5 and minus 1. Oh, so sorry, 1 and divided by 1 minus 0.9119 and times 5. Okay, and what is the value?
It is 70.38.
Yeah, 70.38. Now, step 3, we want to find the critical value of f. We have level of significance is 0.05, and we have the degree of freedom for the distributions is 5, and 40 minus 5 minus 1, which is 34. Yeah, and what is it? The
Is
critical
two
value.
2.49.
Yeah, 2.49. Now, please compare the value of observed f and critical value of f.
Fs is greater than F alpha, so we reject it null hypothesis.
Okay, so we reject HO. Okay, we reject HO and we say that the model is significant. Oops. The model is significant at 5% level of significance. Okay, so that is our conclusions about the overall test, the overall significance of this model. So we do the test, we calculate the test statistic, we find the critical value of f, and we see that the observed value of f is greater than the critical value. That's why we reject the null hypothesis and we conclude that our model is significant at the level significant of 5%. Okay. All right. Thank you, Bảo Anh. Any questions here? Any questions here? Okay, it's very clear, right? All right. And as we say, we have one more way to do the test, that is using the p-value approach. Now look at the estimation output here. All right, look at the estimation output here. I wanna, okay. So look at this. Below the number of observation, we have an F here. F with the degree of freedoms of 5 and 34. We have F here equal to 40.37. What is it? What is the value of F here? Do you know? Do you know it? What is it? What is the value of F in this estimation table? It is the observed value of F that you can calculate from step 2. Okay, so look at this. From step 2, you can calculate the test statistic by using the provided coefficient of determination. All right, and you get the value of 70.38. Okay, and here it is the observed value of F. Okay, the observed value of F here, you don't have to calculate it. The model has calculated for you. All right, and as you see, there's maybe a little difference between the value that you can calculate here and the value in the table, because there's maybe some calculation error. Okay, some rounding error. Okay, that's caused some just a little bit different for the value. Okay, and so that's why if you have the estimation table, you don't have to do step 2 anymore. You just look at the table and then you take the calculated F value from this table. Okay, some people may think that this one is the critical value of F, and they compare the value that they got here with the value of F in this table. And that is not correct. Okay, they are all the observed value of F. Okay, there's no critical value in this table. All right, the number in all the numbers in this table are sample statistic, not any critical value here. Okay, so F here is the observed value of F for this model. All right, and below it we have the probability, prof larger than F, which is the probabilities that we can see an F value which is greater than our observed value of F here. Okay, so this one is the probability that we can observe an f value that is greater than our observed value of f. Okay, so the p-value, that is the p-value of the observed value of f. Okay, and our p-value here is very, very small. It is 0.0000, which is very, very, very small. And of course, it is smaller than 0.05. And of course, we can reject the null hypothesis. So here, there is another way that we can test for the overall significance of this model. That is, all right, now I will erase this one. I will write a new one using another way, another approach. That is the p-value approach. We have the hypothesis HO is that R square is equal to 0, and H1 is that R square is greater than 0. Okay, so in step 2, you still have to have the observed value of f, that you can take it from here, which is 70.37. Okay, and we have the p-value associated. Okay, now according to the estimation output. Okay, we have the fs, the observed value of f is 70.37, and p-value of f, okay, the p-value associated with this observed value of f is equal to 0.0000. Okay, and this one is obviously, okay, p-value here is obviously less than alpha, which is 0.05. So from this, we can reject the null hypothesis, and we conclude that the model is significant at 5% level of significance. All right. Okay, so that's how we can use the p-value approach. And as you can see, p-value, we can take it from the table. We can take it from the estimation output. And we already have the level of significance. You just have to compare those numbers with each other to get your conclusions. You don't have to look for any critical value. Okay, so it's very quickly, it's very easy to use the p-value approach, and it is very clear cut. Okay, so sometimes when I ask you to test for the overall significance of the model, but I don't provide you the critical value, then obviously you have to use the p-value approach. Okay, all right, so that is a test for the overall significance of the model. Okay, we still have one more. Multiple linear restriction test, which is test for the joint significance of a group of variables. Now, for this one, first, do you have any questions regarding the test, the overall significance of the model? Any questions here? If not, I will move to the next one. Okay. No? All right. Good.
Cô cái critical tiếng Anh là gì đấy?
Tiếng Việt à? Okay, in Vietnamese, critical value mean giá trị tới hạn.
Cảm ơn cô ạ.
Okay. All right. Okay, next. Test for the joint significance of a group of variables. Now, look at this estimation output. Okay, look at this estimation output. Oops. Why is okay? Now look at this. You can see that as we say, the t here is the observed value of t when we test the individual effect of each independent variables on the dependent variables. Okay, and p-value here is the p-value associated with this observed value of t. Okay, the p-value here. So look at this. At 5% level of significance, you can see that p-value of fair and p-value of the regression coefficient of gas price, they are very high. Okay, they are very high. 0.686 and 0.632. Okay, so compared to the level of significance, which is 5%, okay, 0.05, these p-value are larger than the level of significance. So we can say that we cannot reject the null hypothesis that the regression coefficient on these independent variables is equal to 0. Okay, so which means that these independent variables, fare and gas price, has no individual effect on our dependent variables here, that is bus travel. Okay, so because they have no individual effect on the dependent variable bus travel, you might want to omit them from the model. Okay, you want to omit them from the model. We want to leave them out. Okay, but maybe as we say that there may be no individual effect, but they have the joint effect, like in this case. Okay, like in this case where we have y, this x1, okay, and x1 has a very high correlation with x2, so you can see that here will be our x2, for example. Okay, x2. So although they do not have much individual effect on y, but the joint effect of these two variables is significant. Okay, together they do explain for the value of y. Okay, so here we may want to test before decide to leave these variables out of the model. We may want to test this joint significance of this variable fare and gas price to see together, okay, fares and gas price, whether fares and gas price jointly explains for the variation in the value of bus travel here. Okay, so to do that, we are in doing that, we are testing the joint effect of fare and gas price on bus travel. Okay, that is the kind of test, the type of test we will study here. Test the joint effect, the joint significance of a group of variables, not all the independent variables in the model. If we test the joint effect of all independent variables in the model, that will be the test the overall significance of the model. Okay, but here we just test for the joint effect of some independent variables in the model. Okay, now let's consider the model here. We have 5 independent variables in the model, that is x1 and to x5. Okay, we use x1, x2, x3, x4, and x5 to explain for the value of the dependent variable y. Okay, all right, and we call this one the unrestricted model. Why do we call it the unrestricted model? We will explain it later. All right, and the coefficient of determination for this model is called R squared U. Okay, U stands for unrestricted model. So the coefficient of determination of this model is called R squared U. All right. So now here we want to test the Jones significance of x2 and x4 on the dependent variable y. Okay, maybe we see that there's no individual effect of x1, x2, and x4 in on y. So we want to test the Jones significance of them. Okay, to see if there is the Jones significance of x2 and x4 on y. All right. Okay, so we will test the hypothesis H1, that is beta 2 equal to beta 4 and equal 0, which means that there's no joint effect between of x2 and x4 on y. Okay, so this will be our null hypothesis, and the alternative hypothesis will be that like this. Okay, at least one of these regression coefficient is statistically different from 0. Okay, so here we have now this one will be our restriction here. Okay, the restriction. So this model, we still have x2 and x4 in the model, which means that the model is not restricted by this hypothesis. Okay, this model is not restricted by this hypothesis. That's why we still have x2 and x4 in this model. And that is why we call it the unrestricted model, which means it is not restricted by the hypothesis here. Okay, and now if beta 2 equal beta 4 and equal 0, if the null hypothesis is true, then x2 and x4 should not be in the model. Okay, x2 and x4 should not be in the model, should not be included in the model. So our model here will only use x1, x3, and x5 to explain for the value of y. Okay, so this one is called the restricted model, which means the model is restricted by the hypothesis here. Okay, and the coefficient of determination of this model is called R square R, where R here in the parentheses stand for restricted model. Okay, so here we have two models. One model is not restricted to the hypothesis. We call it the unrestricted hypothesis. And this model is restricted to the hypothesis, and we call it the restricted model. Okay, now let's see how we can test for the hypothesis of whether beta 2 and beta 4 are simultaneously equal to 0. And we say that x2 and x4 has no joint effect on the dependent variable y. Okay, all right. So to test for this hypothesis, we have to follow the following steps. Step 1, you have to state the hypothesis HO and H1. Okay, so it's the same as the as what we do in the test, the overall significance of the model. All right, we have multiple linear restriction here. For this example, we have two restrictions in the null hypothesis. That is beta 2 equal to 0 and beta 4 is also equal to 0. Okay, and the alternative hypothesis is that they are not simultaneously equal to 0. Okay, now step 2, we will calculate the test statistic. All right, so here because we are dealing with multiple linear restriction, then the test we are using will be an F test. We calculate the observed value of test with the formula here. Okay, so we have ESS of the unrestricted model minus ESS of the restricted model divided by M, okay, and divided by RSS of the unrestricted model and divided by N minus K minus 1. So I rewrite the formula and get this one. Okay, all right. And okay, if we divided the numerator and the denominator of by TSS, then we will get this one. We have R squared, the coefficient of determination of the unrestricted model, minus the R squared of the restricted model, okay, divided by M, okay, and divided by 1 minus the R square of the unrestricted model and divided by N minus K minus 1. Okay, that will be our F value. Okay, I will rewrite it here so that you can easily see the degree of freedom of this one. Okay, we have F, the observed value of Fs equal R squared of the unrestricted model minus R squared of the restricted model, okay, divided by M, which is the number of linear restriction in the null hypothesis, okay, in the null hypothesis, and divided by 1 minus R squared of the unrestricted model and divided by N minus K minus 1. All right, so look at this. You can easily see the degree of freedoms of the numerator and the degree of freedoms of the denominator here. Okay, so this F will follow an F distribution with the degree of freedom of M and N minus K minus 1, where M here is the number of restriction in the null hypothesis. So in the null hypothesis here, we have two restrictions, which is beta 2 equal to 0 and beta 4 is also equal to 0. So in this case, M is equal to 2. Okay, and N here is the sample size and K here is the number of independent variables in the unrestricted model. Remember that. Okay, K here is the number of independent variables in the unrestricted model. Okay, all right. So this one will follow an F distribution with the degree of freedom of M and N minus K minus 1. So what will happen to F if our null hypothesis is true? What will happen to F? What will be the value of F if the null hypothesis is true? What will be the value of F if the null hypothesis is true? Where are you guys? What will be the value of F? The null hypothesis states that, okay, x2 and x4 does not explain any for the variation in the value of y. All right. So what will happen to F? What will be the value of F if the null hypothesis is true?
0.
Yeah, 0, right? Because if the null hypothesis is true, which means that the coefficient of determination of the unrestricted and the restricted model will be the same as x2 and x4, okay, does not contribute anything to the explanation of the value of y, okay? So as r squared of the unrestricted model is equal to the R square of the restricted model, then our F value will be equal to 0. Okay, so like in the previous case, so if we want to reject the null hypothesis, then our F must be very different from 0. So here we will find the critical value of F again with the level of significance of alpha and the degree of freedoms of m and n minus k minus 1. All right, we will make a comparison between the observed value of f and the critical value of f. So if the observed value of f is greater than the critical value, then we can reject HO. Also, you can use the p-value approach. If p-value of f alpha, if p-value of fs is smaller than alpha, okay, then we can reject the null hypothesis HO. All right. Okay. So now let's do this for the what is it? For our example here. Okay. Let's do this to check whether we want to here. Let's check whether we want to leave fare and gas price out of the model. Okay. Now, okay, I will do that for you first. Okay. In order to do that, in starter, okay, you will have to. This one is our restricted model. Unrestricted model. We still have fare and gas price in the model. Now I will have to regress the restricted model where we do not have fare and gas price in our model. So our independent variables will be income, pop, and land area. Okay, enter. Here we will get the estimation of the restricted model. This restricted model has an R square of 0.911. Okay, R square here 0.911 and R square of the previous model, the unrestricted model, is 0.9119. Okay, so at 5% level of significance, should we leave fare and gas price out of the model? Should we omit them from the model? Please do the test. Okay. So at 5% level of significance, should we leave fare and gas price out of the model? Should we do that? Follow the step that we discussed here. Okay. Any volunteer? Any volunteer for this exercise? If you have any questions, that just turn on your mic and ask me. Any volunteer doing this exercise? No one? Okay, so Diệu Linh nào.
Can I try?
Yeah.
Yeah. So we see that the r square of u is equals to the r square of restricted model.
All right. Now,
So
we have the step here.
yeah.
Okay, we have the step here, so just follow the step.
So the step 1, we need to state the
Yeah.
hypothesis.
Okay, so step 1, we need to state the hypothesis, which is H0 and H1. So what is H0?
The H0 is the beta of
Okay,
sphere.
so beta, what is it?
Sphere.
Okay, maybe we can call it beta 1 and beta 2 for short.
Yeah.
Okay.
So the beta 1 is equals to beta 2 and equal to 0.
Yeah. And
For the alternative hypothesis, the beta 1 square plus beta 2 square is greater than 0.
okay, good. Now in step 2, we have to calculate
The test statistic.
the test statistic. So what is the Fs?
The Fs is
R square.
calculate by
Yeah, we have to use the formula to calculate the the observed value of F. Now we just write
r square of u minus r square r
here.
multiplied by n minus k minus 1
Yep. Divided by.
divided by 1 minus r square u
Yep.
multiplied by n.
Yep. Okay, and just plug in the number. We have R square of the unrestricted model is 0.9119. Okay.
0.919 minus by 0.9119.
And minus 0.911. 911 is the R square. Look at this.
Yeah.
We have 0.911 here is the R square of the restricted model. And 0.9119 here is the R square of the unrestricted model. All right. So here we have 0.9119 minus 0.911 times
40
yeah.
minus 5 minus 1.
Yeah.
Yeah.
Minus 5. The number of independent variables of the unrestricted model. Okay. Minus 1. Remember that K in this formula is the number of independent variables of the unrestricted model. All right. And divided by 1 minus
0.9119
yep, and times
times
M is the number of restriction in the non-hypothesis. How many restriction do we have here in the non-hypothesis?
2.
Yeah, 2. We have 2 restriction here. Okay, that is beta 1 equal to 0 and beta 2 equal to 0. Now, what is the value of F here?
We got it approximately 0.17.
17. All right. Okay. So now step 3, you have to find the critical value of f, which is f alpha equal f of 0.05. We use level of significance of 5% with the degree of freedom of 2
Of 2
and 30,
and 35.
30 34.
Yeah, a 34.
Yeah. So what is it? Just look it up in the in Excel. What you get? Can you find it?
I'm trying to.
Yeah, use the function app.inv.rt. And in the parentheses, please provide the level of significance and the 2 degrees of freedoms.
Yeah. The first degree of freedom one is like the
Yeah, that is the numerator degree of freedom. That is 2 in this exercise.
it's equals to 3.27 to 2.8.
3.27, 2 by what? 3.28?
Yeah, it's like 3.275. So I got it like 3.28.
3.28, all right. Okay, 3.28 here. Okay, now step 4, please compare the value of the observed value of f and the critical f. See that? Fs
Yeah,
is,
we see that Fs is smaller than critical value of F.
yeah, and then
So so we do not reject the null hypothesis.
reject HO. Okay, then our conclusion here is that we should or should not.
We should we
Yeah,
we
we should. Okay, leave or omit, leave the 2 variable out at 5% level of significance. All right. Okay, because we do not reject HO. We cannot reject HO, which means that, okay, we do not have the enough evidence to say that fair and gas price has a joint effect on our bus travel. That's why we should leave the two variables out of the model at 5% level of significance. Okay? Okay, thank you, Diệu Linh. All right. Do you have any questions here? Guys?
What is m like is like the number of the parameter in the hypothesis, right?
Yeah, the number of restriction in the null hypothesis, you can see that here, although we have just one line, but we have two restriction here. Okay, we just we have decomposed the restriction here. We have beta 1 equal to 0 and beta 2 equal to 0, which means that we have two restriction in the null hypothesis. Sometimes you may want to test for the joint effect of three independent variables. Then you may have beta 1 be equal beta 2 equal beta 3, and they are all equal to 0. And that's in that case, you will have three restrictions in the null hypothesis. Do you got it? And also, you can say that is the number of parameters in the null hypothesis here. Here we have two parameters, which is beta 1 and beta 2. Okay, so M is also the number of parameters in the null hypothesis. Okay, or we can say that is the number of restrictions in the null hypothesis. Okay. Any other questions? All right. Now, next, this is how we do it in paper. Okay, do it manually. But here in Starter, you can use a command to test for the joint significance of fair and gas price. All right. Now, but in order to do that, you have to regress the unrestricted model first. You have to regress the unrestricted model first. Okay, like this. This is our unrestricted model. Then, after you have run the regression of the unrestricted model, you will type the following command. Okay, now you want to test for the joint hypothesis of fair and gas price. Then you will type test, and then you put fair and gas price after. Okay, we test fair gas price and then just enter. Okay, then you will get the copy as pictures, delete, and then you will get the result here, test fair and gas price. Okay, we have two restriction here. That is, the coefficient on fair is equal to 0, and the second restriction here is the coefficient on gas price is also equal to 0. We have, and Starter has helped us to calculate the F statistic. The test statistic here, the observed value of F, which is 0.17, is the same as we calculate by using R² of the two models. Okay, and also the probability associated with this observed value of F is equal to 0.8415, which is a very high number. And of course, at 5% level of significance, okay, at 5% level of significance, this p-value is greater than the level of significance. And that's why we cannot reject the null hypothesis. Okay, we can reject the null hypothesis, and that's why we may want to drop out these two variables. Okay. All right, so in Starter, you just type the command test, and then the independent variables you want to test for the joint significance of that. All right, that is how we do in Starter. All right, that is for linear restriction model. Sorry, linear restriction test. Okay, next, do you have any questions regarding this? If not, we will move to the next one. That is, we want to test for the linear combination of the regression coefficient. Okay, no questions. All right, let's move on. Okay, now we want to test for the linear restriction of the regression coefficients, and the most typical type of test here is to test for the equalities of two regression coefficients. When we want to test for the equality of two regression coefficients, which means that, oh, I want to know whether the effect of these variables on the dependent variables is the same as the effect of these variables on the dependent variables. Okay, for example, now, oops, okay, so for example, you may have, okay, so the test, the linear combination of regression coefficient. Although here we have to deal with many regression coefficient, okay, but it is not a multiple linear restriction test because we only have one restriction in the test. You will see. Okay, so what is a linear combination of the regression coefficient? Okay, so a linear combination of the regression coefficient will be look like this. We have A times beta I plus B times beta Z. Okay, this one is equal to C. So this one, all right, this one is called a linear combination. A linear combination of the regression coefficient beta Z and beta I. All right. So this linear combination will be equivalent, okay, to this. We have A. Con phải học tiếng Anh, con bảo án trong đâu thôi, con chỉ thi chuyển án trình thôi. Just wait a minute. Đợi, đợi tí nữa các con. Let's go out. Okay, so this combinations is equivalent to A times beta I, okay, plus B times beta Z minus C is equal to 0, okay, where A, B, C here are constant, okay, are constant, and beta I and beta Z are the regression coefficient of the model, all right, and then we want to test this one, although here in the combination you can see that we may have two regression coefficient here, but we have only one restriction, that is this combination is equal to 0. So that's why we will not use f-test anymore. We will use a t-test, like what we do in the testing regression, testing the individual regression coefficient. Okay, we will consider this one. Okay, we will consider this one as an individual regression coefficient, and we will conduct t-test for this one. Okay, all right. And the most typical type of testing the linear combination of regression coefficients is that one. We want to test whether beta I is equal to beta Z, which means that whether the effect of xi on y is the same as the effect of xj on y. Okay, and here we have the alternative hypothesis. If you want to conduct a two-sided test, then we will have the alternative hypothesis like this. We have beta I is different from beta z. Okay, you can also conduct a one-sided test, like a right-sided test like this. We have HO beta I equal beta z, and H1 is that beta I is greater than beta z, which means the effect of xi on y is greater than the effect of xj on y. Or you can also conduct a left-sided test like this. We have beta I equal to beta z, and the alternative hypothesis is that beta I is smaller than beta z, which means that the effect of xi on y is smaller than the effect of xj on y. Okay, so here this hypothesis is equivalent to what? Okay, this hypothesis is equivalent to HO. We have beta I minus beta z is equal to 0, and H1 is that beta I minus beta z is different from 0. Okay, all right, so we consider this one as one individual regression coefficient, and we will conduct the t-test for this one. All right, so if we consider this one as an individual regression coefficient, we will conduct the t-test as follow. We will have to calculate the t-test statistic, the observed value of t. How can we calculate the observed value of t? Do you remember the formula to calculate the test statistic, the t-test statistic? We take what?
We take the beta j hat
Okay.
minus beta j star divided
Yeah.
by the standard error of beta j hat.
Yeah. Right. Correct. So we take the observed value of beta z hat minus the suspect value and divided by the standard error of beta z hat. So here, if we consider this one as an independent regression an individual regression coefficient, we will calculate the t for it. By that, we take beta I hat, the observed value of beta I, minus beta z hat. Okay, and minus the suspect value here, which is 0, and divided by the standard error of beta I hat minus beta z hat. Okay, so here we have, do you still remember the formula to calculate the variance of AX plus BI? Remember that? We have a formula to calculate the variance of AX plus BI. Here we have A equal to 1 and B equal to minus 1. Okay, and X here is beta I and Y here is beta Z hat. Okay, so here we have to calculate the standard error of beta I hat minus beta Z hat. Okay, in order to calculate that, you have to calculate the variance of beta I hat minus beta Z hat. Okay, use this formula, the variance of AX plus BI, to calculate the variance of this one, of beta Z hat minus beta I hat minus beta Z hat. Then just plug in the number you get, you will get the observed value of t for this exercise, for this test. And then you just have to find the critical value of t and find the rejection zone, okay, and make the conclusions. All right. The most important step here is to calculate the observed value of t. All right, and the most complicated test here is to calculate the value of t, and in order to do that, you have to calculate the standard error of beta I minus beta z hat. Okay, now look at the slide. Oops. Look at the slide. We want to test the equality of two regression coefficients. Now let's consider the model. We have y here is equal to beta 0 plus beta 1 times xi, and so on to beta 5 times x phi and plus y. This is our model. We want to test. We want to see whether the effect of x2 of x3 on y is the same as the effects of x4 on y. All right, so we will test the hypothesis like this. We have HO is that beta 3 equal to beta 4, and H1 is that beta 3 is different from beta 4. Okay, and this hypothesis is equivalent to this one. We have HO is that beta 3 minus beta 4 is equal to 0, and H1 is that it is not equal to 0. All right, so the test statistic here, we will take beta test statistic. We will take the observed value minus the suspect value and divided by the standard error of the observed value of the estimators. Okay, so in order to test it, we still have to follow 4 steps. Okay, step 1, we want to establish the hypothesis. Step 2, we want to find the test statistic, where we have the standard error of beta z hat minus beta 3 hat minus beta 4 hat. Okay, I forgot this one. We must have what is it? We must have a star here to stand for the suspect value. Okay, this one is the suspect value, and in this case we have the suspect value is equal to 0. Now, where with standard error of beta 3 hat minus beta 4 hat, okay, is equal to the square root of variance of beta 3 hat plus variance of beta 4 hat minus 2 times the covariance of beta 3 hat and beta 4 hat. Remember that this one is the covariance between the two regression coefficients. Okay, the covariance between the two estimated coefficients. All right, and for this one, in order to calculate this one, do you know the variance? How can we get the variance of beta 3 hat? Where do we take it? The variance of beta 3 hat? Where do we get that value? In the estimation output? What do we have here? So in the estimation output, we have the standard error. To get the variance of beta 3 hat, you just have to take the square of the standard error. This one is the same. For the covariance of beta 3 hat and beta 4 hat, what you have to do here is to use a command in starter. In starter. In order to find the covariance between the regression coefficient, please use a command that is VCE. Okay, VCE. After you have regressed the model, you run a command that is VCE. Okay, and enter. All right, you will get the covariance matrix of regression of the regression coefficient. All right, copy as pictures. Now delete this one and paste this one here. Here we have the covariant matrix of coefficients of the regress model, which is the beta hat. Okay, remember that this one is the covariant matrix between the coefficients, not the variables. All right, so in the here we have this one is the covariance between the beta hat of fair and beta hat of fair, which is the variance of beta fair hat. Okay, and this one, look at this, we have gas price and upper we have fair, which means that this one is the covariance between the beta hat of fair and the beta hat of gas price. Okay, and the same for this. We have income here and fair, which means that the covariance between the beta hat of fair and beta hat of income is 0.8335. Okay, all right. So these are the covariant matrix. And you can find the covariance of those regression coefficients by looking at that matrix. And fill the number here, just plug in the number here, you will get the standard error of the regression coefficient of this one. And then find the critical value of t and compare the value of ts to tc and draw the conclusions. All right. Now, for this one, I want to compare the effect of maybe income and land area. All right, I want to compare the effect of income and land area on bus travel. Okay, whether the effect of income okay, now I want to find some but in order to do that we need some positive numbers so that it will be easy for you to do that. No, not this one. I will try another one. I will clear this one and I will use another data set. I will use maybe this one, which tool that you have used in the practice exercise for chapter 2 and chapter 1. Now I want to regress wage on ASU, expert, and IQ, for example. All right, and I want to compare the effect of ASU and expert. All right, look at this. You can see that in this sample, the effect of ASU on weight is greater than the effect of expert on wage. Now, help me to test. You already have the data, right? Now you start to help me to find the answer to these questions. So is the effect of ASU on wage is greater than the effect of expert on wage at 5% level of significance? Okay. Now help me to answer these questions. To test for the following hypothesis, the effect of ASU on wage is greater than the effect of expert on wage at 5% level of significance. Now, any volunteer? I need to do this. Any volunteer? Right? So I will have you to solve this problem first. All right. So here we want to compare the effect of education on wage and the effect of experience on wage. Okay. So our hypothesis here, we will follow 4 steps that we have been talking about. Okay. The step 1, we need to state the hypothesis, which is beta HO and H1. So our variable here, AU1 expert, we may call this one beta 1 hat and this one beta 2 hat. All right. So our hypothesis here is that beta 1 is equal to beta 2. And H1, we want to know whether the effect of AU on wage is greater than the effect of expert on wage. We have beta 1 greater than beta 2. All right. Now, in step 2, you have to calculate the test statistic. Calculate the test statistic. Okay, we have T is equal to beta 1 hat. Okay, this one is equivalent to beta 1 minus beta 2 equals 0, and beta 1 minus beta 2 is greater than 0. We have beta 1 minus beta 2 hat and minus the suspect value, which is 0, divided by SE of beta 1 hat minus beta 2 hat. Okay, so where SE of beta 1 hat minus beta 2 hat. This one is equivalent to the variance of beta 1 hat plus the variance of beta 2 hat and plus 2AB times the covariance of beta 1 hat and beta 2 hat. But because B here is equal to minus 1, then here we will have a minus sign. Okay, minus 2 times the covariance of beta 1 hat and beta 2 hat. Okay, now look at the estimation output. Look at the estimation output. We have the standard error of beta 1 hat is 7.09626, okay, which is, so the variance will be 7.05626 square plus, what is it? The standard error of beta 2 hat is 3.115545. 3.115545 square minus 2 times the covariance. The covariance, and in order to find the covariance, we have to use the command VCE. Okay, we have the covariance matrix of the regress model, of the coefficient of regress model. We have the coefficient between the covariance between beta AU hat and beta expert hat is here. We have 8.9426054. Maybe we call it 8.943. Okay, 8.943. Còn 20 với phần xong chưa? Rồi ra ngoài chưa học xong mình là just wait a minute. Okay, now please help me to calculate this one. What is the value of it? Use your calculator. What is the value of it?
Six point four.
6.4506.
6.4506. Okay, thank you. Now, step 3, we have to determine the critical zone, okay, the rejection zone. What is it? The critical reason, we have T alpha. Critical value is that T of 0.05. And what is the degree of freedom here? Well, the degree of freedom is 931. Okay, 931. Now, what is the value of it? Look it up in Excel. What is the value of it?
Minus 1.64.
Oh, not a minus, but because this one is a right-sided, then we have 1.64.
Yes.
Yeah, 1.64. Okay, so here we have the rejection zone. The critical reasons will be from 1.64 to infinity. Okay, so as you see, oh wait, I forgot to calculate the test statistic. All right, so this test statistic here, we have beta 1 hat, which is 58.1. Okay, 58.1 minus beta 2 hat, which is 70.42. 17.42 minus 1 and minus 0 divided by this one, 6.4506. What is the value of this? TS?
6.31.
6.31. All right. So obviously you can see that the observed value of T, okay, fall into the rejection zone. Okay, the observed value of T fall into the critical region. So that's why we have T fall into W. That's why we will reject HO. And we can conclude that, okay, so the effect of, so beta 1 is statistically greater than beta 2, or we can say that the effect of, education on wage is greater than the effect of experience on wage, all right, at 5% level of significance. Okay, that is how we compare the equality of two regression coefficients. Okay, any questions here? All right. Okay. Actually, we still have one more thing about the prediction. All right, but it's quite not so long. We will talk about it in the next lecture. Okay, today we study the multiple linear restriction test and the test of a linear combination between the regression coefficient. All right, so just at home study the exercise. You can, here I have an example here, an exercise I take from the books. You can, yeah, you can do this one at home. Okay, and if you have any questions, you can ask me. All right, next time we will study the prediction. When we know the value of the independent variables, we can estimate, we can predict the value of the dependent variables. Okay, all right. Any questions?
Teacher, our group sent you an email for group work. Can you check it?
Okay, I'll check it later. I will have the next class at 12:15, and after that I will check it. Okay. All right. Any other questions? Okay. Practice at home. Okay. Then we will study prediction in the next lecture. All right. So see you on Wednesday, and have a great weekend. Bye bye.
Teacher,
Yeah.
I and Hậu
Yeah.
has bonus point. Have you?
Yeah. All right. I will take here. Sorry, I forgot that.
Thank you.
All right. So we have Bảo Anh and Diệu Linh, right? Bảo Anh, Võ Huyền Bảo Anh, not. Yeah, encourage Khói and Diệu Linh. Phạm Vũ Diệu Linh, đúng không? Yep. Okay. Right.
Thank you, teacher.
Yep. So goodbye and see you. Bye bye.
Goodbye.
Sorry, teacher. Sorry,
Yeah.
teacher. I have a question for the group work.
Yeah.
Yeah. When we use the hypothesis, we have to use the p-value to determine whether it has an effect or not. So when we use the f-test, is the p-value one tail, right?
Yeah. Right.
But in the table derived from the data, it is the two-tailed p-value. So do we have to take it divided by 2?
Oh no, for the F test, we only conduct one tail test, okay? And that's why in Stata, the p-value for the F value is also one tail, okay? One tail p-value. Remember that. The right tail p-value. For F test, we only conduct the right-sided test. So that's why in Stata, the estimation output of Stata and any other econometric software, the p-value for F is always one-sided, the right-sided p-value for F.
Okay, thank you, teacher.
Yeah. Right. Any other questions? All right. So see you. Bye-bye.
Goodbye, teacher.